we're going to have a webinar on partial discharge and UHF partial discharge detection. As you may know, the partial discharge is one of the aging indicators of insulation, or any insulation in any electrical equipment. You know, any electrical equipment in the world has some kind of insulation, and that insulation is a vital part of any electrical equipment, and without insulation none of the electrical instrument or equipment or apparatus would work. So looking after insulation and insulation problems is very, very important and paramount in electrical industry, and partial discharge is one of the good indicators of insulation health, and is a very good diagnosis tool for insulation assessment. So go to partial discharge concept. Okay, by definition, first we have to see what the exact definition of partial discharge, because without knowing the exact definition, we wouldn't be able to exactly know what we're doing. So partial discharge by definition is localized, incomplete, consistent, and synchronized discharges, internal or external to the insulation, and are early warning of insulation failures. So when we say localized, we mean partial discharges can occur in some parts of the insulation, not all over or all across the insulation. So they are localized. That's the first important part. Then they are not complete, they are incomplete. So they are not flashover, or the path for discharge is not complete. So they happen partially. Then they are consistent. So they happen whenever the sinusoidal wave or the voltage goes up in positive or negative cycle, and they happen. So they are consistent, because sometimes for some reason you might have some discharge, but it must be just one time, one off, and doesn't happen consistently. So partial discharges are consistent. Fourth is they are synchronized with the power network voltage, because the main reason the partial discharge are happening is the voltage of the power supply. So they definitely must be synced with the power supply, because with the rise of the power of the voltage in positive or negative cycle, when we get to a point which is called inception voltage or starting voltage, the PD will start. So they are definitely synchronized with the power supply voltage. They can be internal or external to the installation, and they are early warning. So PD is not something like it, I mean, you cannot energize your instrument or equipment. You can energize, and equipment might work very well without any problem. But PD is a early warning. So if you have a PD, depending on the level of the PD, your insulation might have a limited lifetime. So you have to be aware of that. Okay. Partial discharge physics. Partial discharge can be due to many reasons physically. One is the voids inside your insulation, inside the mass of your insulation, for many reasons, either for manufacturing defects or something, or either by some physical defects which happened, or by electrical means, mechanical means, or any other reason. But they are isolated voids inside your insulation. They can be sharp, irregular surface on your conductors. They can be like electrical string inside the insulation because of many reasons. Or they can be external, by some floating metal, by some sharp points at positive or at the conductor, or by some sharp points at ground level, or they can be surface discharge. So all of these defects, physical defects, can lead to partial discharge, which is not good for your insulation, because partial discharge creates heat and can lead to spot burning, I mean internal spot burning or surface burning, and ultimately flash over and end of life of your insulation and your equipment. Okay, partial discharge measurement concept. So how we do measure the partial discharge? That's very important to understand this bit, because when we say partial discharge, what we're looking for? We're looking for physical defects, actually. And that physical defects might be many of them inside your installation, because it's a random thing. So you might have millions, or not millions, maybe thousands of or tens of hundreds of thousands of small voids inside your installation, but you're looking for the biggest void, because you don't care about the small ones. You're looking for the biggest, which is the most dangerous. So when we say partial discharge measurement, so we're looking for some kind of capacitance or discharges. And we know the unit of discharge or charge is coulombs. But because PD is very low in terms of coulombs, we normally deal with picocoulombs or nanocoulombs. So by measuring the amount of discharged charge inside or outside the installation, we actually measure the size, the physical size of physical defects inside or outside your installation. So partial discharge is measured in terms of picocoulombs or nanocoulombs, if they are really big. So that's the unit of partial discharge, which is unit of charge, actually, which gives us which is an indication of the physical size of the defects of insulation. Okay, if we don't look after partial discharge, that could be the consequences, because partial discharge is a gradual distracting phenomena inside your installation, and after a while that partial discharge might lead to complete flashover and just puts an end to your installation. Either it's a cable or transformer or breaker or bushing or surge arrestor or any kind of equipment which has insulation. So looking after PD, measuring PD and monitoring PD is a crucial job of any maintenance team in any plant. It's very important. Okay, PD and aging process of equipment is like a bathtub curve. So by this bathtub curve, we mean we might have some infant mortality in our insulation or equipment, but after a while we get to a steady state failure, which is the middle age of your equipment. And then after a while, with aging of your equipment, the failure rate becomes higher again. So this bathtub curve most probably is true for all of the electrical equipment, including partial discharge, including failures due to partial discharge. Okay, partial discharge measurement techniques. So how do we measure partial discharge exactly? That's a problem, because without measuring partial discharge, we won't be able to assess the situation. So we have two different techniques for measuring partial discharge. First is analog techniques, which pretty much now outdated. They used to be used before this digital technology, but now these days we use digital measurement techniques. So the difference is, in analog technique you deal with the analog capturing, not actually capturing, analog measurement, which is mostly based on peak measurement of the PD impulse. First rectification and then peak measurement and filtering of the PD impulse. So in analog method, you pretty much measure the biggest partial discharge and the peak of the all discharges happening inside your installation by totally analog techniques, analog filtering, analog measurement, and things like that. So this technique is not used anymore as far as I know, but these days we use digital measurement technology. In digital measurement technology, we capture every single impulse activity. So when a single impulse, either a PD or anything happens, the system captures and makes an image of that partial discharge, and then syncs that image with the voltage supply. And that's why we call this technique PRPD, which means phase resolved partial discharge. By phase resolved partial discharge, we mean we capture a single impulse in the, any single impulse, and then we map or graph that single impulse against our voltage. So that's called PRPD, which is, used these days for partial discharge measurement and detection, measurement, and assessment. Okay, phase resolved partial discharge is something like that. When it comes to reality, we have our sine wave and we have the dot pattern, and in terms of the frequency of occurrence of those partial discharges and dot patterns, we have a graph, a color graph like this, or like a spectrum. Then we can see exactly what's happening inside the installation by these dot patterns and figure out which kind of partial discharge we have, where is it, and filter it by new and the latest filtering technology and digital filtering technology. It's quite a powerful tool in partial discharge measurement and assessment. Okay, measurement techniques of partial discharge when it comes to the offline and online. So we have offline measurement and localization techniques, which we have to switch off our insulation, switch off pretty much and isolate our insulation and put our auxiliary and external power supply, which should be PD free, or the PD level should be below the anticipated PD of the equipment. And then we energize the test object and measure the PD. So that's offline measurement. We have online measurement and monitoring, which we install permanently our partial discharge measuring equipment like quadrupoles, voltage dividers, and everything. And then we just monitor and measure the PD online and continuously. And then we have online surveying. So by online surveying, we mean we check and survey all the site, and then we pinpoint some partial discharges in the equipment. That's the third. So we have one offline method and two online methods. Okay, online PD surveying techniques. So by surveying, we mean just checking all of the site and plant, and then pinpoint and look for some expected partial discharge. And for these we have three techniques. The first technique is acoustic partial discharge surveying, which is the first basic one, but it's mostly effective for external partial discharges, which is really audible because we need the acoustic signal emitted from the partial discharge, and it's mostly used for power lines and with dangerous partial discharge levels actually close to corona, because you should be able to hear them, or either by your ear or by some dish or microphone. So that's the first basic method. The next method is VHF partial discharge surveying. So by VHF, we look for the frequency map and image of the partial discharge in a VHF frequency range. The third and the best one is UHF PD surveying. So we look for partial discharge images in the ultra-high frequency, which is pretty much the best of this all online partial discharge surveying methods. And the frequency range is from 100 megahertz up to a few gigahertz. Okay, when it comes to partial discharge impulses, we know from the mathematics of, not sure high school or uni, but every single impulse has a frequency image. And the sharper the impulse is, the wider the frequency band. So we know the corona and surface partial discharges are very long in time. So they are in the range of 100 nanoseconds. So the image is pretty much in the lower range of the frequency, which is VHF. But we know internal partial discharges, when they happen in the range of 100 picoseconds or something like that, which are really sharp. So the frequency image is most probably in the higher range of the frequency spectrum, which is UHF. So by UHF scanning of the instrument or the equipment, we are able to map and detect the internal partial discharges, or better say it this way, UHF technology and UHF partial discharge detection methods are very effective and useful for internal partial discharges. Okay, why we use UHF PDD? First, because it's an online method, so any online method is preferred to the offline methods, because for offline method you have to switch off all the instruments and cables and everything, which is quite difficult or might be even impossible in most of the cases. But online methods gives you that tool to check and assess the partial discharge without disconnecting or de-energizing your equipment. So, but compared to VHF methods, the UHF method is not prone to noise, because most of the noise happens in the lower frequency range or close to VHF. So any VHF method is very, very sensitive to noise. But one of the biggest advantages of UHF method, that UHF method is not so sensitive or prone to noise, because no noise can happen or happens in the UHF frequency range. And then, so the UHF PD is one of the best tools and techniques, and we can scan the wide area of the UHF method. It's pretty much like photography of your whole site, and then look into each photo and see what could be wrong with any of the parts or equipment. And one of the other advantages of the UHF PDD is it uses variety of sensors. So either VHF, UHF, either transformer plug-in, either antennas, or everything. So that variety of sensors gives you the good tool for scanning and checking and pinpointing every kind of partial discharge. So Megger UHF PDD is our latest new product for UHF partial discharge detection, and it's quite a good tool and has it all pretty much. So because it does quick surveying for MV and HV plants. It's very quick, really. It scans everything. It's touch screen. It's very easy to work with, though it's got buttons, but touch screen is pretty much easier in most of the cases. Longest battery power, up to 10 hours. It's vital, because without battery power you wouldn't be able to walk and scan the site that much easily. So variety of sensors, as we talked about, is very important. Gives you good tools to scan everything, and it's got PRPD, which is phase resolved partial discharge feature, and it can be synchronized with main by variety of techniques, and uses and utilizes that PRPD, which is very important in partial discharge assessment and detection. It's dual channel for comparison purposes, because comparison is one of the best tools for partial discharge assessment. It's got freeze function, again for comparison purposes, because you can do some frequency spectrum imaging, freeze that, and then do another one and put them together and compare them, see what could be wrong. And it's got the internal partial discharge generator, which helps you to check the instrument quickly sometimes. Okay, UHF partial discharge user interface, 3 main menus, and the procedure is pretty much like that. So in the first menu, you have the spectrum analysis, or you work in the frequency domain. What happens is you scan the whole frequency from 0 up to 1 gigahertz and get the frequency image of your site of any partial discharge which might be happening. In the second step, you get the frequencies of interest. So by frequency of interest means suspected frequencies, which you might have PD. Then you select that suspected frequencies and then go to time domain, which is pretty much phase resolved partial discharge. So in time domain, you get the real actual the picture of partial discharge, physical, real picture of your partial discharge in time domain or phase resolved. Then you can have a look at the pattern and everything, say which kind of PD is it. Then the third step is to go to level measurement and check the level and stability of the level of the partial discharge. So those three menus are pretty much the main menus of the UHF PDD. Okay, what's in the package? In Megger UHF PDD package, we have the main unit as we talked about. It's very light, it's robust, it's got bigger screen, carrying belt, touch screen, easy menus, USB port, battery operated. So you have the main unit, which is pretty much used for working with, saving data, connecting and everything. Okay, then we have a variety of accessories which needs to be available for exactly and effectively work with the unit. So first we have two antenna types. Both are UHF antennas. First we have a bipolar antenna, which is a bipolar, actually a double antenna. The feature is it can scan a wide area. So for scanning the area, the bipolar antenna is much more effective because it can see a wider area or wider space for partial discharge. And then we have unipolar antenna. This is again UHF, but unipolar antenna is mostly effective for pinpointing when you're looking for the PD. So you suspect some PD, you hear something, and then you aim your unipolar antenna and walk around to find the exact PD point. So those two sets of antenna are UHF antennas, which are very important for PD scanning, surveying, and pinpointing. Then we have a UHF capacitive sensor, which should be put in between the earth of the instrument and the ground. So it is very, very effective. It's like it can be installed permanently for online monitoring purposes. So you can install tens or hundreds of these on any equipment you want to temporarily monitor. And then once in a while, you can just connect your UHF PDD and check that specific or one by one and check if something is wrong, and then save the image and compare the image and do the fingerprinting and things like that. This is UHF and it's very, very effective for internal partial discharge detection and can be used almost everywhere. It can be used temporarily or can be used and installed permanently. Then we have a range of HFCTs, either permanent HFCTs or clip-on HFCTs. So depending on the application, those HFCTs can be installed and used for partial discharge detection. But HFCTs work for in VHF frequency range, so not UHF. Then we have the TEP sensor, which we use for MV or LV switchboard PD surveying and scanning. So if you want to scan or survey inside your MV or LV switchboard, you have to just put that TEP sensor and move it around and listen to it and see if you got any partial discharge inside, because any partial discharge will create a transient voltage in the body on the earth of the switch gear or switchboard, sorry, and then you are able to assess and monitor the partial discharge. Then we have the main sync modules, because they are very necessary and vital for phase resolved partial discharge. So for partial discharge, for PRPD, we need our instrument to be synced with the voltage supply. For syncing that, we need a variety of modules depending on the application. We have three of that modules. So in terms which you can just sync your instrument with the power source or voltage supply of the site, which is very important for PRPD. So then we have other complete accessories. We have other complete accessories like headphones for listening to the partial discharge. We have transit case. We have installation accessories like brackets, nuts, bolts, braids, and accessories like that for site installation of your accessories like that capacitive sensor. Then we have battery charger, HF connection cables, and the demo box. And that demo box is good for office training purposes without going to the real site, so and do an office demo and training at office. So it's a complete package, and it's got almost everything for for UHF partial discharge detection. Okay, now the procedures, how we really work and assess or check the partial discharge. So the first step is a spectrum analysis. So by spectrum analysis, we just scan the whole frequency for partial discharges. So that's the first step. We should first do a full frequency spectrum capturing or spectrum analysis. Then we have to look for suspicious frequencies or frequencies of interest. So we have quite a variety of techniques to look into specific frequencies of interest. So frequencies of interest means some frequencies with the maximum and average level are very different. So because if it's just noise, the average and maximum should be close. But if it's partial discharge, the maximum should be quite considerably apart from the average. So everywhere in the frequency spectrum, you have a big gap between the maximum and average. That frequency is suspicious. You have to select and pick up that frequency and just zoom into that frequency and go to time domain and do your analysis. Okay, what are the frequency detection? Because frequency detection is very important. When you do a spectrum analysis, you have to be able to pick some frequency and then zoom in that frequency and listen just to that frequency and analyze that frequency. So quite a few techniques for frequency detection. First is difference between max and average, which we talked about. Second is freeze function. So by freeze function, you do some frequency spectrum, freeze it, and then move around or change something, and then do another and put them and overlap them together, and then see what's the difference, and then look into the frequencies. Second is two-channel comparison. So you have two channels, you can compare two channels and see what's the difference, and then look for the frequencies of interest. The other one is simply frequency windowing. So you just select frequency or frequency band from the lower frequency to the upper frequency and scan the frequency manually, or do the frequency windowing and check each frequency separately, see what's the difference. Okay, freeze function. Freeze function is very effective at site because and the procedure is like that. So you stay away from suspicious equipment which might have PD. You will stay away normally between, say, more than 15 meters. You do one scan or frequency spectrum, and then and freeze that, and then you get close to the instrument as close as possible, and then do another scan and put them together and see what's the difference. If we have a difference, it means we have some PD in that equipment. So you can zoom in the frequency, go to time domain, and do more analysis. Okay, the second step after that frequency spectrum analysis is time domain analysis, or PRPD analysis. So we pick a frequency and then go to time domain and look into time domain for the PRPD pattern, which gives us that real partial discharge physical happening inside or outside your instrument. That's the second thing. Okay, time domain analysis is very effective because PD is always in sync, not always, but 99% of the times PD should be in sync with the voltage supply. It could be 2D pattern, 3D pattern, and then we can assess the shape and the pattern of the PRPD partial discharge and say, okay, which kind of partial discharge we have. First, if we have a partial discharge. Second, which kind of partial discharge and which type of partial discharge we have. Is it corona? Is it void? Is it cracking? Is it something else? Okay, but we should be aware. Sometimes we have some noise misleading because they are in sync with our voltage supply, because with some switching power supplies using thyristors or IGBTs or something, they trigger and send pulses exactly in sync with our voltage supply. So like PD, they might be in sync. We have to be aware of that. But partial discharges has always inception and extinction voltage levels. That's the difference. And then the next step is to go to the level assessment. So we go to the level assessment and we check the level and how stable is it and how periodic, and check the level of the partial discharge. So a few practical examples of phase resolved partial discharge pattern. This first one is corona partial discharge. As we see, the corona is mostly happening in the lower range of the frequency, and in the higher range of the frequency, we don't see corona. So the frequency of the corona is limited to at most 300 megahertz, and it's depending on on the negative or positive or ground or voltage. The shape might be in the positive cycle or negative cycle, but corona is mostly in the lower, mostly detectable in the lower range of the frequency. So the small voids inside the insulation pretty much are spread all over the frequency and can be seen in all frequency ranges. But they are different from corona. They discharge in higher du over dt when the derivative and the derivative of the voltage is the most compared to the corona. So UHF versus RF or radio frequency or VHF. We know the most of the noises happens in the VHF or radio frequency. So UHF is that has that advantage over RF or VHF, as we can see from this practical example. So in the RF we have a very noisy all over the place partial discharge pattern, but in UHF we have a nice clean partial discharge without any noise. And we have used our UHF capacitive sensors for this. Okay, again, so UHF and VHF partial discharge phase resolved pattern for corona, for voids, and for surface partial discharge. As you can see, they have different patterns and different images for different frequencies. So this kind of patterns needs a bit of experience. When you do partial discharge, have a look inside and check and compare different patterns to figure out which kind of partial discharge we might have. Okay, conclusion. So UHF partial discharge is the most effective quick. It's not like a perfect which can do everything for us, like when we switch off like offline partial discharge, but this one is the most economical and the most effective and the quickest way to detect dangerous partial discharges and localized partial discharges. So it's very economical, it's very quick, and it's very effective without any disconnecting or discharging or switching off your equipment. It's new and it's easy technology. It's very easy to work with this instrument compared to the other, techniques, which is really can be quite a challenge. And it's most effective and noise suppression tool. So by this UHF, we don't care about the noise because we don't work in the noisy area. And we can use that PRPD with this instrument, which is very effective, and look into different partial discharge patterns and everything. And it's an online method, which is a big advantage. And we can scan a wide area and a variety of installations, which is quite important. We can just scan the whole site in a few minutes, or a whole plant in a few minutes, and look for some PD and pinpoint that. And it's the most economic one compared to the job it does. So yeah, it's a very powerful tool for partial discharge detection. Okay, gents, that's the end of the show. Hope you've enjoyed it. So any questions I can take, and then we go through the presentation. Okay?
Thank you very much, Cameron, for the
Thanks,
useful presentation. We'll wait and see if there's any questions for us. If there's any questions, please type it into the chat field, and we'll be happy to assist. And also, if you would like to request any demo equipment, please let us know, and Cameron will be arranging that for your behalf.
Okay, thanks, Ahmed, for your nice comment. Thanks very much.